Ja, lieber Carlos, vielen Dank.
Dear Carlos, thank you very much for this perfect introduction. Thank you also for Tobias Schlichtmann, representative here for the entire Board of Management of NAMUR, for this invitation. And a special thanks, of course, also to Christine Oro Saavedra and Birgit Fischer for the fantastic organization of this event. Ladies and gentlemen, on behalf of the KROHNE Group, Dagmar Dirzus and I, Attila Bilgic, would like to welcome you all to the 88th NAMUR General Meeting. We are delighted to be sponsoring this event, and we wish for everyone to have an inspiring, informative, exciting event today. We would like to take this opportunity to express our sincere gratitude to NAMUR and its member companies for their significant influence on the development of the KROHNE Group. Let's continue to shape the future together. Currently, of course, we're in a difficult time, a time of the third year of recession, inflation, rising costs and low growth rates. But to secure prosperity, wealth in Europe in order to stay ahead of the game and ensure that Europe continues to be a technology leader and attractive production site, we need to do things. So, are we set up for that, says Dagmar? Our innovative capacity is lagging behind. And compared to its GDP, EU only invests half as much as the United States, for example. As a result, 17 times as many large corporations were created in the US as in the EU over the last 50 years, with their market capitalization 70 times higher. And what's behind this difference? A greater willingness to take risks. What we need here is a fail-fast mentality that allows for rapid iterations and experiments rather than trying to create rules for even the most minute detail in advance. Unfortunately, a safety-first mindset, when exaggerated, can lead to bureaucracy, which slows us down. The EU is the leader in regulation. 13,000 new regulations were issued since 2019 compared to 3,000 in the US. What we need is significantly more venture capital and a culture that accepts entrepreneurship and failure as a learning process instead of stigmatizing every mistake. And finally, we need to make sure that the excellence we have in research is tied in much more closely with the industry so that we can put innovative ideas onto the road much quicker. What can we do specifically in the process industry, Dagmar, to ensure long-term productivity and profitability in Europe? In the process industry, we need to invest intelligently and purposefully in digitalization and AI-supported process optimization, leveraging the existing wealth of data. This will enable us to increase the efficiency of our plants in Europe and offset at least part of the higher energy costs. Greater autonomy and smart production facilities are one step in the right direction. Production efficiency can be significantly increased, for example, with predictive maintenance or the optimization of process parameters. Another way smart systems promote efficiency and productivity is by freeing up expert capacity, by relieving specialists from routine and bureaucratic tasks so that they can concentrate on activities that create value and increase productivity. Modern systems afford us an opportunity to break down silos by improving data transparency, making data visible from production to administration. They create a consistent basis for communication, where previously there were many different isolated solutions. Of course, AI is not the cure-all, but it can certainly help. What exactly do we have to do? We, as companies, need to strengthen our innovative capabilities. One way to do this is by forming strong partnerships between companies and research institutions, as KROHNE does, along with players such as Evonik, Lanxess and many others. And one of the most powerful partnerships is NAMUR. The standards we develop together are invaluable. Just think of modular setups with standardized interfaces according to NAMUR MTP, or networking in the field with the help of the advanced physical layer. Without APL, the NAMUR open architecture really isn't much fun. However, with all these technologies, we're still far from being autonomous. What milestones, Dagmar, do we need to achieve for autonomous operation? We discussed this with a number of representatives from the chemical industry and defined 3 crucial milestones. First one is connectivity. That's the basic prerequisite for complete digitalization and networking. What it means is the seamless integration of all field devices, sensors and actuators into one communication network. Without such a digital infrastructure, all further steps would become extremely difficult. We need systems, plants that offer sufficient power in the field and interactive measurement and control devices that can be integrated. The second milestone is what we called beyond diagnostics. Of course, many of us currently don't have the money available for large investment projects, but that's exactly why we really need to exploit the potential for efficiency gains now. For example, with plug and produce for field devices, simpler system integration, predictive maintenance, of course. Beyond diagnostic means that a measuring device doesn't only measure its own parameters, but it can also predict irregularities in a production process, and if several such field devices pool the information they generate, we will certainly be able to bring planned and unplanned downtimes down or prevent them entirely. And how will that make us truly efficient? To become truly efficient, we have to go even further than beyond diagnostics. Interoperability is the crucial concept here, meaning the seamless interplay between all the involved players, plant operators, component manufacturers, service providers, and of course, the interplay and interaction of plant operators amongst each other. To achieve this, it's essential to define and apply standards. Process X is a project that shows how such interaction can be achieved. At least at the last NAMUR main meeting, Felix Bass, Udo Enster and Björn Hoper demonstrated this using the predictive steam consumption use case. Standardized data exchange via the asset administration shell is another key. We will be hearing more about this later on in this presentation. This step then leads us to the third milestone: intelligence in every measure. This milestone means maximizing relevant plant insights. Insights are based on data and know-how, and the ideal place to combine data and know-how is the digital twin of a plant, to which we as component manufacturers contribute with our own digital twins. And this is the basis for process improvements. Artificial intelligence can then provide support to us as a process advisor. Yes, Sabine Pegel last year presented the different levels at which AI models can already be used in an advisory capacity for a batch plant at Covestro, from combing through regulations to error diagnostics to process optimization. She was also able to report on the first autonomous operation of a subsystem in a plant. In other words, AI can already be a smart advisor for us, constantly making suggestions for improvement. At some point, self-optimization of plants will be real based on this. Okay, admittedly, there's still a long way to go until we get there, but where would we be without visions? These three milestones, connectivity, beyond diagnostics, and intelligence in every measure, will take us from today's level of automation to fully autonomous plants, step by step. The route is laid out clearly for us. The technologies are available, and now it's on us to walk the talk. What's keeping us at the moment isn't so much a technological hurdle, but hesitation. We are seeing great examples where we've made good progress together with our partners, and we'd like to show you some of those today. Let's get two of these partners onto the stage, Thomas Schavitis from Evonik and Ulrich Christmann from Lanxess. Thomas, you could make the start. Please join us up here on stage. So, Thomas, welcome. You're an enterprise domain architect at Evonik. Welcome with us up on stage. I'm delighted to be here too. Thomas, you've brought us an example that may be typical for countless similar plants in the chemical industry. Absolutely, Attila. It's a classic technicum system at Evonik. What does technicum mean? Well, Technicum is a technical center where process engineering processes can be developed and optimized in a test environment. And how does such a technicum benefit you? Well, we need to become faster and more efficient in optimizing our production plants. The technicum is one way of achieving that. It allows us to glean as much information as possible through a limited number of tests that we can run. It will increase the amount of information in future. Well, that sounds really great. Which process are you testing in this example? In this example, we're testing a catalyst process. The aim is to react as much hydrogen as possible with a liquid via a catalyst. In order to do this, hydrogen is fed into the liquid under high pressure. This creates gas bubbles. For a stable reaction, it's important that the composition of this multi-phase flow remains constant. And how do you ensure that? Through continuous flow measurement. For this process to work well, we need a high flow velocity, which produces small gas bubbles. Now, these small gas bubbles in the multi-phase mixture must be reliably detected by the measuring device. If the mixture is correct, then the measuring device displays a green light. And what happens if the flow velocity becomes too low? If the flow velocity is too low, the gas bubbles are larger. That, of course, reduces the reaction surface on the catalyst, and this is a negative impact we don't want. The measuring device is now used to accurately detect such a situation, and it does. What we can see here on the blue is the blue display, and I think that's quite amazing. We've got a multi-phase mixture, and the modern Coriolis measurement device can measure the liquid with the enclosed gas bubbles so precisely and reliable. Yes, measurement technology has made a leap in progress. Indeed, a lot has happened, enough to automate a single process. But at the technical center, we're taking things one step further. We want even deeper insights into the process, and that's why we build these systems. And how do we gain these deeper insights? More data, much more data. So more sensors? Yes, that too. But it's not just that. We don't just need the data to gain, or the systems to gain data, we need them to control the process. We are now using what we basically initiated 10 years ago with your presentation on NAMUR and APL. Both technologies are now mature and available. But we're not using the technologies to their full potential, I believe. The data that they make available, in order to unleash their full potential, we need to enrich them with context from the start. Okay, well, let's take another look at the technologies in questions. NAMUR aims to make production and device data easily available and safe to use, especially for plant and device monitoring, but also for optimization. Core automation, with its 4 automation levels, remains largely unaffected. The transmission of production and device data this way bypasses the automation levels, taking data either directly to the cloud or an on-premise database solution for further processing. NAMUR and APL with Profinet have been around for quite some time. But to support you in your goals, we have also implemented APL with OPC UA together with Phoenix Contact in your technical center. Can you explain in a bit more detail what we did there? Oh, of course. Let's take a closer look at the automation topology here. We equipped part of the plant with APL. APL enables the use of modern protocols such as Profinet or Ethernet-APL. In our technical center, the values we measured and the device data are transmitted via Profinet through the APL switch to the control system and the master control system. What's new and what we've now implemented is a second channel. The second channel uses the OPC UA protocol. OPC UA also runs on APL. KROHNE, and this is the innovative part, has implemented an OPC UA server directly into the field device. This way, this allows for the structured, secure and manufacturer-agnostic transfer of device and process data, completely bypassing the different automation layers. Later, we will also do this with PA-DIM. The big advantage is that with this example that I'm showing now, data can be fed directly into an SQL database where we evaluate the data in parallel with the control system with the help of Grafana. Oh, thank you for this explanation, Thomas. At this point, a quick note. We have also implemented the gas bubble detection system on a demo model directly on the left-hand side of the exit, so feel free to take a look. But Thomas, when planning the system, you wanted part of the instrumentation to be implemented with a 420 milliampere connection for various reasons. Could you briefly explain how this works in parallel with the APL installation? Well, gladly. We still, of course, have devices in use that need 420 milliamperes. And of course, these devices have to run in parallel to the APL installation, connected via a regular 420 milliampere connection and heart. So we've been able to keep those running. To run such a solution with the NAMUR Open Architecture, what we use is called a NOAA gateway in connection with OPC UA. This allows you to draw additional information from the field devices outside the control system, just as you would with the APL technology, but of course with greater effort and lower speed than with the APL. Certainly a good solution for brownfield sites. But is there a difference between the data transmitted via Profinet and those via OPC UA? Well, basically, no. The data we transfer with Profinet is actually identical to the data we transfer with OPC UA. But first, Attila, maybe we could briefly explain what data we're talking about. Okay, so we have an example here of a Coriolis device as an example. Data includes both measurement results and device internal information, such as the coil current, which could indicate a change in the viscosity of the medium, or data on the gas content enclosed in the medium. So we're talking both about device and process data here. But you just said that we can transfer the same data via OPC UA and Profinet. Where's the advantage? Well, in the vast majority of cases, not all of this data is stored in the control system, as the effort involved would be far too great, and the data is not needed for the process control system. But now, with the NAMUR Open Architecture, we have all the data shown here and can transfer them directly into the SQL database for evaluation. Well, that makes sense. And what happens to the data? Well, in the first step, to begin with, we have now gained significantly more information from the existing measuring devices. In addition, with APL and OPC UA, we have the option of easily integrating additional field devices that are not directly required for process control, but for data acquisition. This immediately provides us with much more in-depth knowledge about the process we are testing with the pilot plants. and it makes it easier for us to evaluate the data. All the data we glean is evaluated, and we use the findings directly to improve the processes while they are still in the experimental stage. This brings us one step closer to our goal of chemistry controlling chemistry. Do you have an example of this that you could use to explain it? Yes, of course. Here in this image, we see Grafana. In Grafana, all the data we have harvested from the process is correlated by our process engineers and data analysts. They do this immediately, and you can see this quite well on the image. And they give the data additional context, for example, from process analytical information, and then displayed on dashboards. And you can see it here in the two curves at the top left. These are temperature graphs. That's right, the temperature curves seem to be running against each other. Exactly. And that allows us to draw conclusions about the actual process flow. This simple example shows us the value of having free access to data that is not important for process control per se. It requires great analytical effort to get that information. To better understand how these changes in data are linked to changes in chemical processes and what influences these changes, that needs not just the analytical effort, but also intuition and experience. And this is where artificial intelligence can help us with a huge amount of data to identify the correlations and interplay which we need in order to make process adaptations faster and more purposeful. So, Thomas, what's the conclusion from this? Well, Attila, the conclusions are always drawn at the end. In principle, all the additional information that we can now gain gives us much, much deeper insights into what's happening at a chemical level. And this is what is going to take us to the next step. Well, thank you for taking us to your technicum. And we can see images of it here. And thank you for joining me on stage. Now that we've talked so much about technical possibilities, let's take a look at a very specific technology. Another one we've been talking about for over 10 years, the asset administration shell. The asset administration shell is another crucial building block on our way to interoperability and autonomous plants. Dagmar, what exactly does the asset administration shell have to offer? The AAS finally offers us the opportunity to easily install devices and instruments in plants and manage the related documentation throughout the life cycle in a very easy way. Taking it one step further, the asset administration shell will also allow us to almost immediately and automatically integrate devices at every level of automation and control. Again, Dagmar, do you have a practical example? Oh, yes. Let's take another look at the flow measurement in the pilot plant. The Asset Administration Shell, or AAS for short, is a standardized digital representation of a physical or logical asset. In this case, we're looking at a Coriolis device. The AAS provides all relevant information about the entire life cycle of this device in a structured and, what's more important, machine-readable format. Think of the asset administration shell as a container that is usually composed of a large number of submodels. And this precisely is what makes the asset administration shell so flexible and expandable as well. Each submodel addresses a specific use case and contains all the necessary data for this specific case. One of the submodels is the digital typeplate. This, by the way, amongst other things, addresses the EU's requirements for the digital product pass. Manufacturers store standardized device data here, and you can see a physical example on the right-hand side. All the information required for a digital typeplate is stored here. This contains all the information assigned to the device, such as the tag name, serial number, and date of manufacture. This allows the device to be uniquely identified and tracked throughout its life cycle. Another central submodel is what is called handover documentation. This submodel contains the entire documentation assigned to the respective device. So, calibration and material certificates, operating instructions, data sheets, approval documents, and similar types of documents. And for each of these documents, a complete set of metadata and categorizations is stored, allowing the operator to automatically file each document in the appropriate place in their document management system in an automated way. This does not only save time, but it also prevents errors. So the asset administration shell is a very important information tool. Well, not just that. It's also not a one-way street. Data can also be written back from the corresponding assets to the asset administration shell. Data on modifications, on maintenance, repairs, for example, can be stored in the shell in a machine-readable format and written there. This means that operating personnel has access at every time to all the relevant information about a device. During recalibration, for example, the person performing the examination and the calibration can see all calibration stamps since installation. Well, how does that work? Okay, let's take another look at the automation topology at the Technicum plant. And now we add an AAS server that you can see at the top right corner here, clearly located in the operator's IT landscape, securely separated from the OT. As a rule, the operator will store all asset administration shells there. So the first use case is the installation of a new field device. Yes, and when a new field device is delivered, it is scanned at good receipts via the identification link. And we can see this here in the bottom in this little animation. This automatically triggers a process. The submodels of the asset administration shell are imported from the supplier's AAS server to the operator's AAS server. Next, all the contents of the submodels that have been released are automatically stored in the relevant automation systems. For example, the asset management system of the operator is updated with new documentation, or firmware updates are delivered directly to the field devices. This happens fully automatically without the operator having to manually trigger these processes. Simply by connecting the new field device to the APL switch, it makes itself known to all the other relevant systems via OPC UA. And what's the return path for the flow of information back? Well, for example, critical status data can be written back to the asset administration shell during operations. This means that in accordance with NAMUR Recommendation 107, the device statuses can be stored directly from the field device into the asset administration shell in the plant asset management submodel via APL and OPC UA. Communication with the AAS server is accordingly bidirectional, allowing the asset administration shell to unfold its full potential. And how does the asset administration shell support repeated calibration in an external laboratory? It can, absolutely. Calibration by a service provider is a challenging example of a life cycle instance where data need to be stored. Let's take a closer look. The field device is immediately identified in the service provider's control system at the calibration laboratory. This is done simply by connecting the APL switch via OPC UA. The system obtains all the data required for calibration directly from the device's AAS. To do this, the operator grants the service provider restricted access to the corresponding submodel. After the calibration process, the calibration certificate is generated in a machine-readable format and is automatically stored on the operator's AAS server. All service personnel now has immediate and unrestricted access to it. Wow, that simplifies matters immensely, but it does pose questions of IT security. Well, at least we can reduce the source of error known as human error with it, but you're right about IT security. But the next part of this presentation will deal with another form of security and safety, functional safety, the direct protection of people and the environment. And of course, in context with functional safety, the question is, how can more information, more data that we can gain from an asset administration shell support and promote functional safety? So how can an asset administration shell make operations more simple, make it safer, and particularly more autonomous? Okay, well, let's look at one practical example of this. Concentrated sulfuric acid is used as a catalyst in the production of high-octane fuel components. An overdose of the acid can lead to safety-critical situations, in the worst case, to an explosion due to an exothermic reaction. To ensure exact dosing, safety functions often have mass flow meters.
When you exceed the predefined limit values, the safety control will automatically steer the emergency shut-off valve in order to interrupt acid input. Okay, understood. But how can we make sure that the safety function is sufficiently reliable? Well, safety functions are subject to periodic tests, which are prescribed by law. In the event of a fully fledged inspection, both components, shut-off valve and flow meter, have to be removed so that they can be tested with regard to their correct functionality on test benches. The amount of work is immense and it requires production shutdown. For this reason, for measuring devices and actuators, so-called partial tests were developed, which can run the safety control automatically. On the screen, you can see the presentation of a safety loop, a safety circuit, for the implementation of a safety function. It consists of a measuring device, a shut-off valve, and a safety control. Traditional field devices in SIL operation do not allow for hard communication in order to protect devices against non-authorized changes. Modern field devices, however, offer the option, namely that a safety control, even in SIL operation, can be activated via HART. It is now possible for a safety control to put SIL devices in simulation mode. This is how current loops can be automatically tested, including the complete wiring route. A new start of the device is also necessary, in the course of which further integrated test algorithms can be run in order to verify the status of the device. This automated partial test allows for a high level of testing of 70 to 80%. And this contributes to a situation where intervals of the fully fledged test in which devices have to be removed and be tested on a test bench can be considerably extended. But how, in the area of functional safety, can we contribute further to autonomous plants? Let me share my thoughts with you. The first thought is about monitoring software. It is useful in order to efficiently and comprehensively monitor safety circuits and to optimize them. It monitors all the safety circuits in a plant, and it also monitors individual components. In the picture, you can see the HEMA solution. The operator, for example, could look at the history and the results of the periodic tests of individual components and can then proceed to an evaluation. Predefined statistics can be viewed, The history of the individual periodic tests can be viewed. The operator can also see if under certain process conditions typical errors occurred or how frequently certain parts of the plants and the system were requested. The operator can also look at statistics of complete safety circuits in a certain part of the plant, evaluate it and answer the following questions. Under certain process conditions, are there frequent critical situations in which safety circuits were triggered? Or was the plant run too close to safety critical limits? Or were there certain processes in which the periodic tests identified frequent errors of individual components? And what's the benefit to the operator? Now, via the findings he receives via the monitoring software allows for the identification of weak spots and allows for optimization potential. It doesn't only save time, but it also contributes to higher plant reliability. On this basis, we do see an opportunity in the future to identify optimization potential of safety loops on an AI basis, which can then be implemented by the safety officers. Sounds good. But you were talking about a second thought you wanted to share. Absolutely. In the second thought, it is about automated composition and calculation of safety circuits and the connected proof. After the risk analysis has been done, after the tasks of the safety functions have been described, we can then propose a structure based on standardized components, so-called typicals, in an automated way. Measuring devices and actuators bring along all safety-relevant data via the ASS, as, for example, the application-related error rates, SIL evidences, and X evidences. This allows an enormous amount of time saved in the planning and documentation of safety circuits, and at the same time it reduces systematic errors. In the coming years, we also see a crucial further development towards ASS for the functional safety aspect. There is a proprietary ASS for each safety circuit. In this administrative shell, all the relevant data are stored. Structure and calculation of the circuit, all the proofs of the individual components, test instructions, etc. That's not all. The results of the periodic tests, current events, and construction changes are being stored here. This means that the comprehensive documentation and the history of the safety circuits are combined at one point in the administrative shell. Now, we've talked a lot about numerous technologies which can be easily used in the greenfield. Do we see any opportunities to use them in the brownfield as well? Or do we need to invest millions? We've got a really wonderful example we brought along. And this is an example which demonstrates a step-for-step approach. We are going to visit LANXESS and look into the production of TMP. An established production process which is always faced with challenges, but it has got high potential for metrological and data-based optimization at the same time. In this project, together with LANXESS Samsun and the Technical University Dresden, we defined the task to reduce planned and unplanned downtimes. What I can tell you now, it was, and it's still really thrilling. We have learned a lot about turning brownfield into Industry 4.0. Now, for a more detailed insight, we would like to ask Dr. Ulrich Christmann, the Head of Global Automation and Digital Manufacturing with LANXESS, to ask him to come on stage. Please, Ulrich, come and join us on stage. Hi, Ulrich. It's good to have you here, and thank you very, very much for your support. Can you briefly explain to us the TMP system and also talk about the process? Hi, Dagmar. Yes, I'm pleased to do so. TMP is mainly used in the production of resins, plastics and paints. And it comes about in a multi-phase reaction in aqueous phase. And what is the challenge? The target product, TMP, means that salty secondary components come about. The salts dissolved in the aqueous phase lead to a situation where the heat exchanger is subject to clogging, fouling in the evaporation stage. And that often leads to downtimes. And it costs money, doesn't it? What about control? How does it work now? Now, the data produced in the running system are not totally used for information purposes. From the technological point of view, it would be possible, but the flushing today is started by the operators on the basis of their experience. A comprehensive data evaluation can be a basis in this process in order to optimize the process control. That is our target. In a first step, we want to cut by half the process steps and go towards partially autonomous production. And what are the challenges in the process? There are numerous challenges, since it is about a complex reaction with a high water content. This water content has to be evaporated over several stages, and this has to happen in a most efficient, continuous, and trouble-free way. However, energy requests and the input at the inlet are fluctuating because the steam is not only recuperated from the network or the grid, but for energy saving reasons also from other process stages. So it's a non-linear feedback system, is that right? Absolutely. And this contributes to the problem of fouling, which takes place due to overheating at the heat input. If the energy input is controlled only by the water content at the outlet, it means a high water content and more request of steam, and this is what we need to master. Now, you see the fouling characteristic at the heat exchangers here, and it's obvious what kind of questions you needed to answer at the beginning of the project. Yes, absolutely. How fast is the salt deposit in the heat exchanger is generated, and what is the energy loss in the processing? On the basis of existing data, this can not sufficiently be answered, and this is why we identified additionally requested data, and we readjusted instrumentation at certain points. And one of the challenges was the diverse communication landscape, hard Profinet and Profinet via Ethernet-APL. All relevant signal paths, first of all, had to be systematically integrated. Absolutely, and this was the only way how we could close the data gap. The newly integrated devices, first of all, provide additional process data from certain hidden areas of the plant, and secondly, more comprehensive diagnosis data. And this means that not only new individual values, but also consistent context-related process data are created. What happens to the data? And the extended process data are transferred by TU Dresden and KROHNE into an AI-based analysis model. The target is the integration of a learning application which recognizes deviations early enough and which can generate adaptive control processes, which is transparent, easy to understand, and has a direct relation to real process parameters. And one of the deviations that were analyzed is the fouling you mentioned. And here it is about to understand the context between operational statuses and deposit inclinations and to evaluate them. What you see on the picture is 4 different process parameters which were used for an AI-based fouling recognition. It's interesting to see here that on the basis of these data, as you can see at the bottom of the picture, a continuous fouling growth could be predicted. So what is shown in light gray is the flushing. And with the help of AI, we were able to predict it. Although the input data we see at the top did not show any recognizable trends for the human eye. It goes to show that the recognition was only possible due to the complex correlation of data. Artificial intelligence, and especially modern deep learning, can manage to use technologies like data encoder in order to learn these contexts. Human beings can then extract that knowledge and use it as a decision-making basis. Have we seen a first practical success already, Ulrich? Yes, for example, we're able to see that the combination of easing at the inlet and optimization of evaporation strategy in order to avoid deposits could improve the heat exchanger situation. On the basis of the data collected, the load on the facility and the energy input could be adapted, and we could go for preventive deposit avoidance. That is milestone number 3, intelligence in every measure. So we generated a supporting system which does not replace the operator, but supports the operator in the daily decision-making process, especially when it is about complex non-linear process situations. An intelligent retrofit with modern instrumentation manages to do more than only spontaneous transparency. It supplies structural prerequisites in order to optimize existing plants on a data basis and to run them in a partially autonomous way. Now, what we start by way of additionally collected data and system communication will be the basis for situational control strategies, energy optimization, and predictive maintenance. Well, the example shows what intelligent retrofit can do. Yes, absolutely. A brownfield plant, we have a lot of them, has the potential to be transferred into autonomous production. Thank you very much for giving us the insight and for sharing all the information with us. Thank you very much, Ulrich. It was a pleasure. Well, after all these excursions into the world of technical opportunities, as they stand today and as they will look like in the near future, Attila, what do you think about instrumentation in the coming 10 years? We think that instrumentation will continue to further optimize in many, many areas. In other areas, it will be revolutionized. And that has an impact on systems as well. And let me focus on 3 topics here. First of all, the reliability of the measured value. Second, a simplified operability. And thirdly, connectivity. Let's start with number 1. The reliability of measured values or measurements is represented by examples from the flow measurement technology. Coriolis and magnetic inductive flow measuring devices were considerably improved in the past few years on the side of hard and software. Thus, a more efficient and more adaptive improvement of signal-noise ratios was achieved. We are much better in dealing with process interruptions now. With Coriolis measuring devices, the entrained gas management technology has set a symbol and shows how precise mass flow measurement can be, also with included gas bubbles. Thomas already pointed at the importance. Magnetic inductive measuring devices have, in the meantime, achieved a similar performance. Just go and see the demonstrations in the exhibition areas. Both Coriolis and magnetic inductive measuring devices can ideally deal with solid matter in the medium as well. Electrode corrosion in the magnetic inductive measuring devices do no longer disturb the signal-noise ratio situation. In order to further improve measurements, several research projects are ongoing, amongst others, some based on AI algorithms. AI allows access to process situations which cannot be modeled in a closed physical or chemical situation. Then, in number 1, simplified operability. This is about an easy handling of field devices. In the past few years, it was particularly digitalization that gave that area a boost. Field devices can now be parameterized by way of safe Bluetooth connections. Measured values can be diagnosed. Services such as asset management, monitoring, verification, and certification go without saying these days. But, of course, a lot of more smart services can be perceived. The overall documentation management has been digitalized as well. The operator only needs to scan a field device via the Auto ID code EIC 61406 and then has direct and offline access to all the documentation concerning the serial number. Such a documentation management, like in the ASS, was already implemented. A demonstration for this purpose and on smart services can be seen in the exhibition. In the document management, you will also find video-based instructions and installation instructions. That helps to avoid erroneous operations and false installations. Of course, the lack of experience cannot be offset, but the ASS supplies a precious support here. Absolutely, a lot has happened, a lot of progress has been made in order to simplify an operation of a plant. But you were talking about a third point, connectivity. What do you have for us here? Now, connectivity is about plug and produce of field devices. Just imagine the following situation. 4 o'clock in the morning, a measuring station reports urgently required maintenance or there is a total failure. Now, when the maintenance people replace the device, the Ethernet-APL connection of the new field device has to be connected, that's all. And via the already mentioned reports, the new field device is immediately recognized. This automatic recognition was already confirmed by the PCT test laboratory and was demonstrated at the occasion of the APL Congress last year. In the near future, we will go one step further, since in the administrative shell, the most recent device configuration is available. It will be directly installed after confirmation by the operator into the field device, and the plant operation can be restarted within a very short period of time. Information about the replacement of the device will be fed back directly into the administrative shell. Now it's about lifecycle management as well. The automated installation of new patches or firmware updates are possible here. Now, changing framework conditions such as new security requirements can thus be implemented swiftly. If a field device vendor makes available new patches or firmware updates via the administrative shell, these can be installed with the help of Ethernet-APL online. The information about new patches and firmware updates happens in an automated way with the help of the administrative shell concept. So the future of measuring devices and the future of systems in the process industry can hardly be imagined without artificial intelligence. In order to better support process industry in future, we must make sure that measuring instruments move away from pure data sources towards information sources and work together with intelligent conclusion tools. Modern measuring devices already cover a plethora of data, flow rate, pressure, temperature, density, conductivity, etc. In the examples from Evonik and Lanxess, we saw that a comprehensive correlation of data is a clear value added. Following this idea, we could imagine, we as device manufacturers, that further measured values and sensors could be supplied with one single device by way of pressure, temperature, or ultrasound sensors. The established housing forms and installation length would not have to be changed, and the costs would not increase. So we use simple means in order to increase the number of primary measured values, and we multiply with the aid of an AI agent the number of process information. Measured values in one device mean fewer devices with the same number of measuring parameters. At the same time, we receive a different quality of measuring thanks to the correlation of different measured values and the evaluation by AI. Thus, the measuring device in future will contribute to a situation where chemistry can control chemistry, as Thomas said. What would be the next integration step, Dagmar? Now, first of all, I would like to express a yes, but. In order to be able to process all these pieces of process information and to derive predictive maintenance from them, we must also increase the computing capacity in field devices, which allows for the use of AI agents. The existing 4-wire technology and the permanently increasing processor performance are ideal prerequisites. Let me look into the future. Just imagine you could use the AI agent and communicate with a digital twin directly in a way as you're used from ChatGPT. The operator Sarah could, for example, ask the plant, can you give me some information about the operating status of measuring station FIC 4711? Hello, Sarah. Yes, by way of analysis of my sensors, I do see that there's an increasing number of gas bubbles, and the downstream pumps has a variation in the throughput and more switching activities. I do recommend to reduce pump performance by 8%. In a second step, it could be conceivable to use the data from several field devices in order to construct one virtual soft sensor, which could even provide a deeper insight into process-specific aspects. All data from sensors, are they combined with historical data of the same plant? If that is the case, we'll get a comprehensive database for the digital twin of such a system. Such a database is ideal for artificial intelligence. If the process engineer, Julia, asks the AI agent the following question, the heat exchangers show first signs of fouling. Do we have to do flushing as planned or can we wait? Hi, Julia. Based on the current acoustic and temperature data of the measuring station, as well as based on the historical course of the last 12 charges, the fouling rate is still below the critical threshold value. A flushing can be postponed by up to 10 operating hours without losing efficiency. Now, once we have gained trust in the quality of such answers, then we will go a step further. If the AI agent recognizes suboptimal properties of a certain substance, it could propose automatically parameter adjustments or direct intervention in process control. And that brings us to the topic that we started off with today, the path towards autonomous plants. In a third step, we would then end at a potential AI-supported simulation of partial systems based on the data of the digital twin of the plant and the devices. The know-how combined here could represent a clear value added. Now, if, for example, the plant manager Zhao Long asks, do a simulation of 2% less steam inlet at the inlet stage 1. Hi, Zhao Long, simulation shows 70% less deposits in the heat exchanger. Well, we can do better. Well, why not go for 3%? You see, our AI is further advanced. It even speaks Cologne dialect. Let me add, artificial intelligence would develop precious potential if the interplay between human expertise, intelligent measuring technology, and process know-how could succeed. The reliability of measuring technology has to considerably improve at comparable costs, and it can only do so with additional data. The basis for that is to have sufficient energy via the 4-wire technology and communication, for example, via Ethernet-APL, and they exist already. If we want to boost this vision of well-proved speed, we'll probably need 20 years rather than 10. We can't afford that. In order to be successful, it has to happen at the latest in 5, better 3 years. Thus, we transform measuring technology from passive data collection towards active process intelligence. Well, we supplied a lot of facts and showed a lot of findings. And we based ourselves on 3 milestones. Connectivity as an underlying condition, beyond diagnostics in order to collect information about the process, and finally intelligence in every measure as our vision of an autonomous system. We do need the autonomous plant in order to keep production and prosperity in Europe. The even faster implementation of findings requires a coordinated and synchronized approach between device manufacturers and plant operators. Measuring devices have to act as intelligent nodes in the overall system. Furthermore, we need a suitable infrastructure in the field as enabler. APL and 4-wire technology are crucial in order to make available the required energy and bandwidth for edge computing and an extended analytics in the field. These are the prerequisites for data communication which connect the field to the IT world under specific requirements in the process industry. Is that enough for an autonomous system? The technologically requested foundations on the field level have thus been created, but we need more. We also need a cultural change in industry. We need more open-mindedness, more speed, but first and foremost, we need more pragmatism. Well, the conclusion is we are not going to wait for European transparent safety concept or further regulations. We are proactive. Well, let me summarize. Hold in high esteem what NAMUR has generated. We are driving global standards. These are no regulations defined by the political arena, but they are standards supported by the industry collectively. And this is promoting economy by economy. Look into your own company, the new or the old it might be. Wherever you can improve things by way of additional information, go for it. I'm sure you're going to find something, and we would like to support you in doing so. Thank you very much to the whole community, everybody who helped us in preparing that talk. And we wish you a wonderful conference, exciting talks, and especially successful partnerships. Thank you very much for your attention.